back to the crash course, The Reliability of Effective Information in the Sciences. This video contains a summary of what has been discussed in the first half of this course, but also includes some complementary comments on particulars of the topic. So, in this part of the video, we are going to introduce the object of the study, as well as some generalities of what counts as defective data in the sciences. So, first, defective information is an umbrella term that covers cases of partial, vague, incomplete, conflicting, and inconsistent information, among others. Defective information is standardly unreliable. This is, in the large majority of cases, when we recognize that the data that we have is either incomplete, vague, partial, inconsistent, conflicting, among others, we discover ourselves unable to reach the conclusions that we desire to meet, or unable to justify or guide our future actions, but particularly we discover ourselves having the epistemic obligation of rejecting and mistrusting this information that we just discovered to be defective. This in order to remain rational. Good examples of the unreliability of defective data can be found in movie trials. For instance, take a witness disclosing very little information about a crime, or her report being clearly partial or vague, intentionally vague. That really looks suspicious. And as a response to this, it is expected that the lawyers, the judge, the jury, and everybody else involved start mistrusting this person. The same happens if a suspect of committing a crime starts contradicting herself. Then that reveals that she is lying, and this is often seen as an indicative of guilt. Similarly, when we discover that a friend has lied to us, the rational response to that action is to start mistrusting this person, at least in similar contexts. In many different contexts, in the large majority of situations in which we encounter defective data, this data would and should be considered to be unreliable in order for us to remain being rational. Nonetheless, in sciences, scientific information is often defective. And although there are good reasons for still aiming at good quality data, meaning accurate, empirically supported, and relevant information, the defective character of scientific data is not only ubiquitous, but inevitable. In light of this, philosophers and logicians of science have aimed at explaining both the presence and tolerance of defective data in scientific contexts and the relation that these practices have with the preservation of human rationality. One of the main motivations behind the study of defective information in the sciences is that the way in which we react and deal and solve challenges such as the presence of contradictions, vagueness, partiality, among others, can be actually revealing about the constraints, but especially the limit cases of human rationality. The aim of the first half of this course is to provide you with a general toolbox, philosophical toolbox, for the analysis and explanation of those cases in which scientists use and sometimes even rely on defective data and their practices still remain rational. In order to do so, in the first half of the course, we focus only on the ways in which scientists treat defective data within the reason-based analysis that focus on scientific theories themselves as abstract entities, or on the individual scientists' beliefs that were endorsed in particular moments. The motivation behind this choice is that, on the one hand, scientific theories are extremely complex theoretical entities that require also extremely complex formal resources to be simplified and scrutinized in a more or less successful way. So it is not clear which type of language we need, how much expressivity we are going to require for reconstructing even bits of our best scientific theories, and also it's not well determined which type of logical consequence relation we are going to be able to use. All this due to the complexity of what a scientific theory is. On the other hand, beliefs and psychological preferences might have some impact in the way in which defective information is used and especially accepted or tolerated in the sciences. But the scope of such impact is very minimum at the level of establishing certain practices as being rational. Furthermore, a study of the reasoning that takes place when dealing with defective data in the sciences is expected to be informed by bits of the structure and abstract information that we get from scientific theories, as well as by the bits of the beliefs of the scientists that employ these theories. So a study that focuses on scientific reasoning is not a study about logic or pure logic applied to reasoning, but it's a mix of incorporating some epistemology to the logic that we have, as well as some history and some science to it. So now, once we have already decided to center our attention on scientific reasoning, there are at least three main concepts that we have to keep in mind when doing so. First one is sensible reasoning. This means that agents are still able to distinguish between the inferential products of the reasoning that are sensible given a particular context from those that are not. We want to use science in order to know which propositions are going to be true about the world or the domain that we are studying, and so we want to be able to preserve sensible reasoning in the sense that when applying our theory, I want to distinguish which are going to be logical consequences of my theory or legitimate predictions or explanations within my theory from those that are not. So that is the first concept that we have to keep in mind. Second one are going to be inferential patterns. So what does it mean? Very broadly described are the ways in which we relate either beliefs, statements, groups, and propositions, among others, to either beliefs, statements, groups of propositions, etc., in order to reach a particular outcome or a particular type of outcomes. So now, what are successful inferential patterns? These are chains of inferences that help us to achieve particular goals in an optimal way. And what is optimal will depend on the phenomenon that it's being studied, as well as the different constraints of the practices associated to the study of this phenomenon. Now, here comes a note for logicians. According to many non-classical logicians, scientific theories can be and have been defective without thereby endangering the rationality of those who use them. That is what makes so interesting this subject for logicians to scrutinize. The history of science contains sufficient evidence that proves that defects can be tolerated for long periods, and that during this period, scientists have used efficiently their defective theories to describe, predict, and even explain certain phenomena. Considering the above, logicians and philosophers of science have developed three different types of research programs for the study of the use of defective information in the sciences. These types of programs are historical, logical, and methodological. This typology can be found in a paper by Šešelja from 2017, which is going to be linked in the description. Historical programs are programs that have deeply descriptive approach to contradictions, but also other types of defects in the history of science. They concern the question of whether defects are commonly appear in the science, and whether scientists sometimes accept and reason from or with defective information. The best exemplar of this type of projects can be found in Peter Vickers' book, Understanding Inconsistent Science, which is also going to be linked in the description of the video. And in this book, Vickers takes some of the most famous cases of alleged inconsistent science and scrutinizes the historical details of each of them, to the point of concluding that the scientists involved in the use of these theories never believed that the theories were really inconsistent, nor that the elements of the contradictions were equally true. And while the analysis provided by Vickers is extremely revealing at the level of the scientists' exhaustive commitments and how they describe their attitudes, it overlooks the role that contradictions and other defects actually played in inferences associated to the implementation of each of these theories into problem-solving contexts. Take the case of Newtonian early calculus. Even if Newtonian mathematicians did not believe that infinitesimals were inconsistent entities, if their inferential practices were, under certain circumstances, inconsistent, the historical and doxastical approaches are not going to be enough to account of why this was a rational practice, the use of inconsistent steps, for instance. And there is where the second type of research programs comes to the discussion. These are logical programs, which have a more normative perspective, which concerns the question of whether we can rationally reason from an inconsistent or any defective set of premises without ending up in logical explosion or other logical challenges. And if so, how this is possible. A very nice example of how this type of research can be conducted is foundable in Meheus' analysis of Clausius' derivation of Carnot's theorem, which paper is going to be linked in the description, in which Meheus takes a piece of Clausius' reasoning and scrutinizes its logical constraints to later provide the basics of a logic, which is going to be an adaptive logic, that might be the best one for the reconstruction of such a reasoning. There is a third type of programs, the methodological programs, according to which we have to seek for a normative perspective which concerns the role of the standard of consistency, precision, and other virtues in the evaluation of scientific theories and scientific practices in general. These programs can be found in some of the most traditional readings from philosophy of science and its methodology, in which the negative connotation of the facts is scrutinized, criticized, and narrowed. That said, let's move to the different types of defects that we will consider in this course and forget about the note for the logicians. So, we said that we were going to have in mind two broad groups of defects. Ones that we can associate to inconsistency, others that we can associate to incompleteness. So, inconsistency. Let's take two presentations of inconsistency in the sciences. First, a proposition A is either itself contradictory or it contradicts one of the basic principles of the set of data that we have. So, this is, in a sense, a statement that doesn't explicitly show a contradiction, meaning that it doesn't have a negation and maybe a conjunction, but that is something that conflicts with the grounds of the research or conflicts with itself. One example can be to say the square is purely white and purely black. So these two things cannot be properties of the same thing at the same time, or at least that's our basic intuition. And the second example is energy can be created or destroyed, whatever you want, in an isolated system, which in itself is not inconsistent. We cannot see a paradox type of statement here, but what happens is that it conflicts with one of the basic principles of our physical theories. So in that sense, is very simply inconsistent with our theory or with a framework. Now, another type of presentations of an inconsistency in the sciences can be when you have some sentence A together with a sentence B that are both derivable from the same set of data, and there is a way to interpret B as the negation of A. Take the following example. The behavior of the atomic nucleus is classical, but the atomic nucleus is a quantum entity. So, there is no negation involved over there. There is no conjunction relating a statement and its negation, but there is a clear problem if we have the two statements together without adding more information. So first of all, if the atomic nucleus is actually quantum, then the classical laws cannot be describing the nucleus. So we have to explain under which circumstances we are going to combine a classical description with a quantum description of the same object. So only when we add this additional information, we are going to be able to make sense of this as a non-contradictory statement. At the moment, it seems very problematic, but this is a common statement in nuclear physics. So, traditionally, contradictions have a negative connotation, on the one hand from epistemology and on the other hand from logic. In the case of epistemology, they are often conceived as indicators of lies and epistemic errors. To know more about this, you can look at Moore's paper from 1942, which is going to be linked in the description as well. From the logical perspective, contradictions are linked to paradoxes and logical triviality. We say that either a contradiction has no information or has too much information, but it's problematic not only for formal purposes, but for our own reasoning. Now, incompleteness. We are going to consider in this course two presentations of incompleteness. On the one hand, a proposition A is incomplete if it does not contain all the information needed to determine whether it is true or not within a particular theory or particular framework to describe accurately a particular phenomenon. A case of this can be more than one type of neutrinos exist. While the statement might be true or might be false, in order to test it in the sciences, then we need more information. How many types of neutrinos are we considering? How do they behave? And so on and so forth. So at this moment, if we want to design an experiment for testing this particular statement, it doesn't seem that we have enough information in order to narrow it down to an experiment. So the second presentation that we can consider of incompleteness is the fact that neither A and B are derivable, but at least one of them is expected or needed to be obtained. So take the case of the anomaly in the perihelion of Mercury. What was happening is that the theory, Newtonian dynamics plus Kepler's laws, was predicting that Mercury had to be in X point. Or if Mercury wasn't going to be found in that particular point, then a planet would have existed between Mercury and the Sun. So when they tested this hypothesis, they looked at the place that Mercury was expected to be located. Mercury was not there, and they looked for the other planet that was expected to be in between Mercury and the Sun, and they didn't find it either. So there was a phenomenon over there that didn't have a label at the moment, but that was causing that Mercury was not where the theory predicted, nor an additional explanatory phenomenon was occurring, which was the presence of a second planet. So the non-satisfaction of neither these two hypotheses was actually constituting a different phenomenon that Newtonian dynamics was never going to be able to account for. So we needed Einstein's theory in order to be able to explain what was happening there. Now, the distinction between how partial, how vague, and how conflicting certain statements are is going to be a matter of degree, as well as how much problematic they are going to be. And remember that the challenges associated to each of these defects are also going to be a matter of degree. But on the one hand, we are going to consider the epistemic challenges, which will include having unreliable information, trusting false statements, not having enough evidence for moving forward in our inference road, not having enough evidence in favor of particular beliefs over others, and not having enough evidence in order to have robust explanations. So those are going to be more or less the epistemic problems that we are going to deal with when having defective information in scientific context. On the other hand, we are going to have logical problems, which are going to be having irrelevant outputs being drawn, maybe irrelevant elements connected to each other or connected irrelevantly. We are going to have to take care of not having logical explosion or logical triviality, and especially we have to take care of lacking sensible reasoning. So these are going to be the major challenges that we might find when analyzing the presence of defective data in the sciences, and the major challenges that we have to account for in order to defend that the practices associated to the use of defective information are going to be rational practices. That said, let's recap very briefly. So defective data is an umbrella term that groups partial, vague, and incomplete information, as well as conflicting and inconsistent. Here we are going to focus on analyzing scientific reasoning when using defective data in order to see whether we can still preserve sensible reasoning despite of reasoning from or with sets of defective information. And we are doing this knowing that the sets of data are defective. We have recognized different approaches to this problem. Some of them are going to be historically informed, some of them are going to be logically driven, and some of them are going to be normative and methodologically driven as well. But we also can approach this phenomenon from two different subjects of philosophical subjects, either epistemology or logic. But when analyzing the issue from focusing only on scientific reasoning, we are going to need to merge all these approaches. We are going to need to provide explanations that combine epistemological explanations with logical explanations, and that are grounded on these three approaches, on a mixture of these three approaches, meaning historical, logical, and methodological approaches. So that's what is needed for us to be able to account for the rationality behind the use, the tolerance, and the reliability of defective data in the sciences. And we are going to talk about how to do this in the next part of the course and in the next video. If you have any questions or comments, just write them below, and see you soon. Bye!